All right, up next we have Christophe Pacolat, who will talk to us about ROSpace. Is that how you say that?
Right.
Or ROSpace?
Yeah.
All right.
Can you hear me? Can you hear me okay? So my name is Christophe. I'm from Switzerland, Lausanne, and I'm working with the Swiss Federal Institute of Technology in Lausanne. I'm also working with the University of Bern in the Astronomical Institute. And I'm going to talk to you today about a simulator we've started developing to support our mission called Clean Space One. Here are a few things I'm going to cover in this presentation is the background that led us to the development of the simulator, some requirements that we used to make our choices, some of the toolkits we use also as a backbone, some internals, and some aspects about validation. And I'll finish with some outlooks. So first, it all started with the Clean Space One mission. Many of you might know about the space debris problem. It's not new, but it has started getting traction and awareness. We have had few encounters here and rises in a number of space debris, and those are starting to cause a special threat in low and medium-low orbits. We have our own responsibility because we have in 2009 launched Swiss Cube, which is a one-unit CubeSat. It has been up there for now 9 years. It's kicking fine, still responding. But every now and then, the nice folks at NORAD tell us, hey, you just get a conjunction 20 meters, 50 meters, 15, 20. So every time we get pretty nervous that we might be losing our first boy here. A bit of how it was designed. It's mostly a student effort, so this is one of the last teams working on it. And this has been a constant point in our group is that we develop satellites as a way to educate students. So as a next project, we decided, okay, we have to go and get that little boy back. And we started with Clean Space One. It's supposed to be, well, a bit bigger than a laundry machine. And of course, the first aim of the mission is to go catch the satellite and deorbit it. But what we wanted also to do is to raise awareness locally, but also internationally about the problem, and develop key technologies related to in-orbit servicing and active debris removal. As you may know, this is not a very trivial feat because you have to rendezvous with a target that you assume to be non-cooperative, as opposed with on-orbiting servicing where your target might still be responsive. A second challenge we have is that our cube here is very small, so 10 by 10 by 10 centimeters. And the only information we have about its position, because it doesn't have any GPS or GNSS system on board, is the two-line elements and some observation on the ground. I might have some. This is roughly the idea we had in the mission plan. Is first the launch, bring us to 500 kilometers. Carry commissioning, test the critical components, and then starts the proper rendezvous phase where you get information from the ground, try to do a few hops where you gradually decrease your distance to the target, detect it, and then using onboard filters and clever maneuvering, increase your knowledge about its position, and then finally do the rendezvous. Then we have the capture, and finally the deorbiting and atmospheric re-entry. So what happens is that we are working with students, and we currently at the very early phase, so something like phase 0 phase in your parlance. And we have been working with a lot of different breadboards, typically for the capture system. And this doesn't apply not only for the capture system, but many of the components that we have on board, be them algorithms to do the filtering, the processing of the images, and other sensors. And our question is, which platform could help us test everything together, and maybe also do some early tests using orbital mechanics, where you have the camera on one side and a mock-up on another side, and try to do maneuvers that correspond with what you would expect in orbit. This is just some images we managed to capture from the ground. So you see it's very faint, and it wasn't easy at all to pinpoint the object and actually catch it like this. We managed it only once using the telescopes of the University of Bern. So it's definitely not an easy feat. So that brings us to the simulator. How do we... that's what I was expecting. Sorry for the messed up slides. The big question is, what would be the best platform to start about building the simulator? So first is, since we work with students, we want something that is easy to get started with. Our students usually are master students, and they have a master thesis project that lasts about 24 weeks. So we don't want them to spend hours and hours and then weeks getting to learn a system or designing their own platform just to do some testing and then have just half a month left in their thesis to do actual research. We want also something that interfaces very easily with existing hardware, be them COTS, hardware, so cameras, or our own in-house development, the breadboards. What we also need is something where the industry has interest in. So if you develop on a platform that has no link with industry and their hardware, then, well, you're a bit screwed. So I'll just take a step back and then present you here what we first thought what the simulator should look like. We have all the intelligence, all that different algorithms that we think were necessary, target state estimator, chaser state estimator, path planning algorithms, control algorithms, actuators, sensors, and a world model with a physics engine. Typically for us, the sensor models should be elements that either simulate an existing sensor, be it, for instance, a camera, or ground sensors, and provide this information further to the algorithms that we develop. We have on the other side actuators for which we need metals. They're typically so your reaction wheels, your magneto-torquers, attitude thrusters, main thrusters, and so on. So again, here we need to have something that can take a model for such an actuator and link it into a simulator. Just a quick jump in the future is some of the elements we already developed as I speak. And then, of course, we have, as I said, all the different software parts, the parts that will actually be transferred at some point into the actual satellite. And roughly speaking, the idea is that you start developing here in a very easy language like Python. And at some point, you start moving to C++ in the actual implementation on the hardware. And here you have elements that should either exist to support a simulation or elements that will provide you the hardware in the loop context. So if you are aware, if you're coming from a robotics background, then very quickly you will think of ROS, which is a robotic operating system. It is very interesting to us because it's a middleware, and it's based on two main concepts, which is topics and nodes. So a node is just something that allows you to encapsulate your algorithm, your actuator, your sensor. In robotics, for instance, they use a node to control a robot like the KUKA or any other industrial robot. And these nodes listen to messages and then do the processing and publish on their own messages on specific topics. And ROS allows you to do that very easily by defining arbitrary messages and just write an easily wrap around existing hardware that you design yourself. But it has also this very strong community support and industry support to drive hardware. So if you come from this world, you're also going to tell me, yeah, well, it's very nice, but the in-house simulator they provide with it, so Gazebo, doesn't really work in space. It's very nice for on ground with a constant G, but anything related to orbital dynamics is not feasible here. So we need to develop here our own solution, which led us to think what can be a good platform to actually simulate orbital dynamics. Again, we made a little wish list and thought, like, what is relevant for us? And of course, since we're developing algorithms and doing more like research, we want to have something we can really look into, know what kind of models are being used, how they're implemented. Nothing against closed source, but in research, we are more interested in those aspects. Of course, when you get some piece of software, you want something that has a decent documentation. And something that's really critical there is actually validated using flight data. That means we don't want something that runs and has no foothold in reality. We want something that has been tested against reality. So we went around and looked. So two possibilities. First would have been to use either SDK or GMAT, but those are more, if you understood properly, like come in earlier in the design phase of a mission. They're very high level and didn't allow us to connect, at least by the time we did the evaluation, with our own hardware. Then we took the more library approach, where we would really get a library and plug it into ROS, and we came up with 42, Basilisk, TUDAT, and ORCID. So again, the question is which one to go with. Long story short, we did our homework again, and for us, ORCID was the way to go. Even though it doesn't have attitude dynamics, we figured it was very well documented, and also some of our partners were using it. So this might have changed, especially if you're from the University of Colorado. You might tell me, okay, this is now open. That was the state 1 year ago. So how did we go ahead with ORCID? So ORCID has a lot of tools that allow you to do simulation, but we might want to add some other force models and also improve the attitude part of it. So we relied on the builder pattern to allow the generation of additional force models gravity perturbations, thrust models, and so on. We made sure that we can configure very easily the different propagators that we built using YAML files. And yeah, this allows us really to control in a very fine-grained manner every object that is being propagated. What type of integrator you want to use, what the state observer is, what kind of thrust models you rely on, the forces you want to consider when you propagate. So once we implemented it, this is what a typical loop looks like. First, we have the general initialization, where you initialize all the ROS nodes that are required. And then for each, sure, yeah, for each object, so spacecraft object, we initialize one propagator. It allows us to control even more precisely for each object how you want to propagate it. And then once you're in the propagation loop, you calculate the forces and torques that are applied on the object, you propagate them, as well as the position of the object. So how does it translate from the user point of view? Can switch. I'll take here just a very easy model that we implemented, which is the T handle to simulate the Jani-Bekoff effect. Basically, here's just a very simple object that takes into account orbital dynamics and perturbation, has an initial rotation and should behave in a very specific manner, which I'm going to show later. So this object is associated with the propagator. This propagator publishes orbital elements and pose messages, which are then associated with the satellite object. And using the transformation toolbox, we then publish this to the visualization system. This is now how it looks like for the user. He has a nice, to some extent, some nice graphics. Here's this T-bar I was telling you about. We can read all the internals of the object we simulate. So here currently it's just the position and orientation, but if you have a more complex satellites, you could access all the different internal parameters. We have a time control panel that allows us to tell us how fast we want to integrate, what the steps should be, and how fast we want to publish. And this allows you either to run the simulation real time and see what would be happening when you do demonstrations and get a really good feeling of how your objects would behave in orbit, or just run normal simulation where you just want to go as fast as possible. And it would give you this feedback by this real-time factor. The way we actually define all of this is, first, we rely on the system, on the launch file system provided by ROS. So those are XML files, and for each satellite we define, we have a configuration file. So let's say we have our SwissCube here, we have our CleanSpace 1, we can have additional satellites. And then when we work on a specific mission, then the mission will pull in the different satellites you want to use. You can make several copies of the same object and create constellations, or you can have this mission, which is chaser and target. So it really allows you to do things very not necessarily easily, but in a very configurable manner. And since it's all XML and YAML files, you can also script it very easily. This is, for instance, how we would define our initial conditions for the example I showed you before. You give the initial orbital elements, some initial states, some information about how you want the simulation to proceed. If you have a more complex satellite, you can define some sensors. You can define elements that will interact with the environment. Typically surfaces, the shapes, whether it is affected by solar pressure, the drag, and any additional third forces. And then, of course, we can. What's interesting is that we can define our spacecraft in, for instance, SolidWorks, and then import the mesh using STL files. Now you're going to ask me how well do we know whether this actually works? Again, the miss on the slides. For everything which is related to orbital dynamics, we of course rely a lot on ORCID. ORCID has been tested to some large extent with the ATV that has flown to the ISS. We have done our own internal tests using NVSat. And concerning the attitude propagation, we looked at three cases. First is the Colorado State wet experiment, which is a passive attitude controlled satellite. The Johnny Bakeoff effect, which I mentioned before, and NASA transit satellites. It was a very old satellite that had been launched between the 60s and the 90s and used gravity gradient stabilization. Here, just for instance, what the guys at Colorado State measured. And in our test, what we saw so far is that we stabilize much faster than they do, typically within 10 hours instead of 5 days. And our initial current supposition is that our hysteresis model is too simple. So there's still some work to do here. Looking forward, what in the current pitfalls we have is that when you have several spacecrafts that stem from the same model, let's say you have two copies of SysCube and they publish, let's say, attitude data, you need to rename manually the messages to avoid them being mixed up by the others. So they're published currently on the same topic. So we need to make sure that this doesn't happen. This is a known issue. And currently, the way ORCID is implemented is that it handles first integration step. It handles only one force and torque, so one subsystem at a time. We have a pull request here that's ready, and we're currently looking at it. In the next steps, what we're looking at is improve the validation of the attitude engine, make sure that we can move forward in our mission design and be sure of what the simulator provides us with. We're interested in looking at the bridge with Appleseed, which is an image generator. Documentation is never good enough, and there's always a way to improve it. So here we want to try auto-generation using Sphinx. You saw also we need to redefine everything manually using text files and One way to improve this would be to have a GUI tool that allows very easy design of a mission. Finally, CFE, CFS. The reason I mentioned that here is that probably the way our simulator is implemented, it comes at a step before. CFE, CFS, the way I understood it, is really working with actual hardware and allows you to go very low level. And as far as I remember from last year's presentation, is that there is already a bridge between CFE, CFS, and ROS, so it's something we want to look into. And finally, it's link the simulator with GPS GNSS simulator to allow us to broadcast GPS messages. Yeah, thank you for your attention.
I apologize if you mentioned this in your presentation. Did you say what you were using for y'all's 3D visualization?
Yes.
Is that what Appleseed is, or is that something?
So the 3D visualization you saw earlier is RViz, which is a tool provided by ROS itself. And Appleseed is an image generator that allows you to implement your own shader model. And the interesting here is that we can simulate what a camera would see. Right. So you can either work in the actual lab and have your camera look at the target, or if you work in simulation only, you could give a model of your satellites to Appleseed, and he would generate what the camera would see.
Sure. Okay. And so just a comment, I guess. So that Appleseed, well, actually, any of those renderers, I'm guessing a lot of what you will see will be dependent upon your global illumination solution, meaning how much Earth albedo you're getting and how cloudy it is and what sort of Earth model you have and all that sort of stuff. One comment just for you, and maybe if there's any other groups in here, there's one of the problems we've run with our NASA simulations trying to use various visualizations is double precision, because typically we like things in orbit, we'd like them to be driven in orbit, and most of the renders don't have double precision trees. So there is a NASA rendering engine available to the public called Edge.
Okay.
So if you or other groups are interested, that it has a native double precision render, and it's used for Earth and lunar and visualizations of everything in orbit. It can actually go all the way down to the ground. Anyway, I just want to make sure you guys knew it was available, should it help you or someone else in the room.
Oh, sounds well. I'll take notes. But can you implement your own shader models?
No, I think for that part of it, you'll probably be better off. This would probably be a better replacement for RViz and your real-time stuff.
Yeah.
The solution y'all are pursuing for the camera, I mean, you can put your own camera models in there. You can do all that stuff. Whether or not it meets your requirements would be up to you. But it comes with some really, really nice Earth and atmospheric models. Okay. So it might help you with regard to developing that. But yeah, I think for your camera solution, you'll have to do something different.
Yep. Side note, one reason why we're interested also in having very realistic rendering is that when you're in close range with your targets, what we've seen in our in the lab simulations is that well, the cube has panels, solar panels, and at some point the cube is very dark. You don't see almost nothing, and all of a sudden you move in a way that the solar panels reflect the solar illumination into the camera.
So one thing we found. Sorry. So one thing we found, we have a lot of the same issues with spacecraft approaching ISS and things. So global illumination solutions where there's lots of light bouncing around in room, and then anything terrestrial, there's the sky, obviously. But all your shadows in space typically tend to be very sharp and defined, like you're talking about. So it's possible that a graphics engine like Edge or something similar might be sufficient for your camera modeling.
Okay.
But it really depends on your requirements. But you'll probably, I'm guessing the Earth model will be where most of your, anything other than direct light from the sun would obviously have to come from the Earth. So.
I assume yes, yeah.
Well, thank you very much.